All right, today's lecture is going to be going over key concepts of the periodic table. Now, many of these concepts you probably already should have gained knowledge of doing last week's activity, so this lecture is mainly just going to kind of wrap it all together and hopefully pull out the key components from those activities that you completed. Now, the periodic table, before it was developed in its infancy, there was a few different just like the atomic model, there was a few um, concepts that were developed that slowly one person built on the information of the past until it grew and grew until what is now today the periodic table. Now, the first group of scientists, the first thing ever mention of this was that once there was enough elements known and discovered, elements that had similar properties, they started grouping them. And the first grouping system utilized triads, where there were some elements in groups of three. There was at least three elements and multiple groups of three that the scientists noticed that their chemical properties were very similar to one another. So they started grouping them in these groups of three and if they shared similar properties. An example that was the first three noble gases of helium, neon, and argon. Because they were so unreactive and they were gases at room temperature, they had similar properties. They started grouping them into these triad groups. Newlands was the next scientist that discovered something important, and that is when they had a larger amount of elements known and they laid them out in order of increasing atomic mass. What Newlands found out is that if, let's say, one element, element X, had certain properties, if they were to lay them out in cards, the next card that had similar properties, let's say element Y, that there was literally 8 cards or 8 elements that existed between X and Y. And that happened again to get to card Z. So initially, he noticed that there was like every 8th element had similar properties. Now, does anybody know why that is? Why would element X and then 8 elements later, element Y, have similar properties? Why is this law of 8 especially work out initially for the elements that are today in the periodic table? It happens to do with valence electrons. And initially, most of the elements that were known early on were the lighter elements, the more prevalent elements, easier to identify and separate. And if you look at the periodic table, if you go from sodium to the next element family member in that column, okay, which is potassium, okay, and if you go right before that, lithium, you'll notice that lithium is 8 away from sodium, and potassium is 8 away from sodium, another 8. And so this law of octaves works really well initially, but then we get to the heavier elements and we start getting into the D and F block as the periodic table starts to grow in the length of a column. This law of 8 doesn't always work. It just works for the first couple periods. The first scientist that you really have to know is Mendeleev. Mendeleev was a Russian scientist. He is given credit for primary credit for being the first to develop what looks like more like the modern periodic table. It didn't look exactly like that as your textbook notebook pages that I gave you that you have access to look at and read, but it does start at least to show a larger amount of elements and putting in these columns of where they have similar properties and the arrangement of these columns. All right, so a couple of key things what Mendeleev stated. First of all, he stated in his paper that the periodic table is organized by increasing atomic mass. Okay, this is how the periodic table is organized. Now today we know that is incorrect, but he, when he published his findings, said that mass was the primary factor. Okay, the second thing he did is elements that had similar properties he placed them in families or in groups, columns. He placed these elements of similar properties in groups and arranged them by increasing atomic mass. Very much like the periodic card activity you did last week, the first activity. Okay, once you place them in increasing atomic mass, start to put them in groups and align them, you start to see a sequencing pattern. Initially, there's 8 elements to separate them, and then they grow as we get to more and more elements. But this is this concept of similar elements being placed in similar columns and families. A couple of wrinkles to his periodic table that are important. The most important is that he left gaps. He left spaces in his periodic table. He didn't put every known element next to the next known element because he noticed that some of the next element didn't match the element that should have been placed in the next slot. It matched better with one or two elements down in that family. So he left spaces in his periodic table, and he would place an X or a question mark in that. And when he reported his findings in his journal, he said that there must be an element that isn't discovered yet that must meet the criteria of that element in that family. He was able to really predict the property of those unknown elements, and even predict its mass and its chemical behavior. And because of this, very quickly after his findings, within a few years, these elements were discovered. Okay, and one of those elements is germanium, which he called exosilicon. Germanium was later discovered, and it matched beautifully with the predicted properties that Mendeleev said there must be. Okay. One other thing that he noticed is that in his periodic table is that he placed tellurium before iodine, even though tellurium was heavier. Now, this was a direct violation of his law or his rule that the periodic table is organized by atomic mass. And he wasn't quite sure as to why that was the case. He stated in his paper that maybe potentially that the masses of these elements was not fully correct or not right, and that's why it didn't exist. But because of properties, he did properly put tellurium before iodine, even though it was known at the time that tellurium was a heavier element. So, and that was because it wasn't until later on that it was discovered by other scientists, and the discovery of how to figure out subatomic particles, that the mistake that Mendeleev made on atomic mass was later discovered. And that was discovered by Moseley. Of the two scientists in this lecture, Mendeleev and Moseley are the only two that you need to be really concerned about. And Henry Moseley, what he was given credit for is he stated the periodic table is organized not by increasing atomic mass, but by atomic number. And this is why tellurium comes before iodine. Tellurium does have one less proton than iodine does, and therefore it does come before iodine. However, the isotopes of tellurium are heavier than iodine, and that just goes about with what the stable isotopes are that make up that element. Okay? All right, some things about the periodic table now, the current one that we know of today. The first of all, any column, any vertical column is called either a group or a family. A horizontal row is called a period. Okay? And that also gives way with the period is that it tells us the energy level that the valence electrons are located. So for example, if I have an element of 1s2, 2s2, 2p6, 3s2, the highest energy level is 3, and this is something that we were supposed to do last unit, and that is the valence electrons are located in the third energy level. So that tells me that this element would be found on the third period of the periodic table. So it would be in the period that is the sodium element. If you look at the periodic table, Na begins period 3, or the third row. The first row is hydrogen and helium. The row right below that is the lithium row across, and the third row is sodium. So this element should be in the third period or the third row of the periodic table. So by knowing the valence electrons and knowing what energy level they exist on, you can also tell what period it exists in the periodic table. Okay. Groups and families, there are 18 labeled groups. Okay. In the periodic table, the F block, the two rows that are pulled out of the periodic table and at the very, very bottom of all periodic tables, those are not assigned any group numbers because there's only two elements that make up that list. So it's really not a full group because there's only two elements that are in there. A couple other things about the groups. Group number 1 is called the alkali metals. Group 1 is called the alkali metals, and again, that does exclude the element hydrogen. Hydrogen is placed in group 1, but it's not an alkali metal. Actually, hydrogen is a nonmetal. The only reason why hydrogen is placed in group 1 is because it has one valence electron, which all the other elements in group 1 have. But property-wise, it's nothing like the other alkali metals. Okay? All alkali metals have one valence electron, and therefore in the dot structure, let's say for example lithium is an element in group 1, it has got one dot, and you could put that dot either at the top of the element, below the element, to the left, or either to the right. It doesn't matter where you put, but it has one dot symbolizing one valence electron. Group 2 is called the alkaline, like an alkaline battery, alkaline earth metals. It has two valence electrons, like the element magnesium, and it has two dots. And again, those two dots could be put any of the way of the four corners of the periodic table. The only thing you can't do is you can't put the two dots next to each other. Groups 13 through 16 do not have any family names. They're just called group 13, 14, 15, 16, or sometimes they're called the boron group, the carbon group, because it's the first element in that column. Group 17 is called the halogens, and group 18 is called the noble gases. So these four families have names that you are going to need to know. And when I talk about the halogens, immediately you should be thinking of group 17, the vertical group just before the noble gases, the farthest most right on the periodic table. Valence electrons, group 13 has 3, 14 has 4, 15 5, 16 6, 17 7, and 18 has 8. Those are the valence electrons. And again, when something has 3, like boron, it's got 3 valence electrons. Carbon's got 4, so you got 4 dots around it. It isn't until you get the 5 dots, 5 valence electrons, you start to double up, like nitrogen has got 1 double dot and 3 lone dots. Oxygen is in group 16. It's got 2 double dots and 2 single dots. Fluorine has got 7 dots, and something like argon has got 8 dots. 8 valence electrons is the most valence electrons an element can have. Once it has 8, its outermost valence electron shell is full, and it's highly unreactive. Elements want to bond in order to get to 8 valence electrons. Elements like nitrogen, oxygen, and fluorine, because they have 5 or more valence electrons, they tend to gain electrons to get to 8. So the nitrogen family, group 15, tends to want to gain 3 electrons when they bond. The oxygen family, group 16, tends to gain 2, and fluorine tends to gain 1. The halogens like to gain 1 additional electron to become full. The other 4 first groups, group 1, 2, 13, 14, they have 4 or less valence electrons. These elements tend to lose. Groups 15 to 7 tend to gain when they bond chemically, and group 18 does not like to react at all because they are full. Okay? A couple other things about the periodic table. Again, the periodic table, if you look at it, it's chunked into 4 blocks. And you got hydrogen and helium that are sitting out there as well as part of those groups. Okay, the representative elements, now remember, the first block is called the S block, which is groups 1 and 2. Groups 1 and 2 make the S block. Groups 1 and 2, the S block, are very reactive metals. Okay, we'll talk more about in the next lecture about what makes a metal, but they're very reactive metals, and they tend to react by losing electrons, and they tend to be usually quite soft. They're not the hardest metals, and they're very, very reactive. The P block is groups 13 to 18. Okay, and they're over here in the far right of the periodic table, the P block. This group is interesting because it has all the different types of elements. It has metals in it, it has metalloids in it, and it has nonmetals in it. So it has the three types of elements that we have are all located in the p block and in groups 13, 18. The first initial couple of blocks, they tend to be metals, which means they tend to lose electrons. And as you get further right, they tend to be more like nonmetals, in which they tend to want to gain electrons. The D block is between the S and P block, and this is called the transition elements. This is groups 3 through 12. The transition elements are called the D block because we go from the softer, more reactive metals to the harder and less reactive metals that are found in the P block. So the D zone is the transition of the softer S block elements that are more reactive into the less reactive, harder P block metals. And that's called the transition elements, which is the D block. The F block is the very bottom of the periodic table, and that's called the rare earth metals or the intertransition metals. This is called the F block. Rare earth are very important elements. They are used in a lot of electrical circuits and different types of transistors and computers. America had the initial edge in rare earth technology and also discovery and also mining of them. China since then has bought up over 90% of all the rare earth elements and have kind of created a monopoly of the use of them, which is going to make it very interesting as the world continues with if they decide to keep hold of that and not allow different countries to have access to those metals with the technology they're developing. Something very interesting that you might find and want to look up if that interests you. Okay. Lastly, the representative elements are the elements that make up the S and P block. Okay, so the S and P blocks together are called the representative elements. Why representatives? Because we have the very reactive metals in the S block. We have the less reactive P block metals. We have the metalloids in the P block, and we also have the nonmetals that are very reactive all the way to the noble gas that aren't reactive at all. So the representative elements literally represent all the different types of chemical reactivity and behaviors found in the periodic table. The D and F block elements tend to be very similar to one another. They tend to be very similar in size and chemical behaviors, and so they don't change as much throughout the blocks, not like the S and P block where they're changing drastically as we move to the next one to the right, and that has to have a lot to do with the valence electrons. Okay, one last thing you're going to need to finish off this lecture is looking at a periodic table. Now, without using any techniques or the good old 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. This was a sequence you were expected to memorize and be able to do any configuration of any element for that. The snake trick was utilizing something in one of the lectures, but I kind of didn't lecture this year in it because of the fact that you had access to the sequencing of it. But this next activity is looking at, can you do the electron configuration of strontium, okay, by doing what's called just the valence electron configuration. Well, to do that, what you have to figure out is which element in strontium, if we identify strontium, strontium is located right here in the periodic table. And if you number downward, starting with hydrogen is 1, 2, 3, 4, 5. The element strontium is located in the 5th period of the periodic table. And since the S block begins the periodic table, the first row that contain, we know that the valence electrons of strontium has to exist on the 5th floor. And since the first two columns of the periodic table is the S block, we know that strontium's valence electrons are found in the 5s orbital. So the valence electron for strontium is 5s, and since it's in group 2, the second column, that means it's got not one electron but 2 electrons over because it's 2 over in that row. So the valence electron configuration of strontium would be called 5s2. Okay? Now if you don't believe me, you could go through the whole configuration of strontium. Strontium has got 38 valence electrons, and you could go through the whole sequence of it. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. After 4p comes 5s, 5s2. And if you count, that's 38 electrons, and the valence electrons are found on the 5th energy level. 5s2 is the valence electrons. So we don't necessarily have to do the whole configuration to do the valence electron configuration. We can just look at what row or what period the element exists on, and it always begins with an S. So 5s, after 5s comes 4d, after 4d comes 5p. The D block always trails by one letter. It is not matching the 5 or 5th floor because it's always one behind and when we fill it. Okay? But strontium has got the valence electron 5s2. So what group is it in? It is in the second group, or group 2, because it has got 2 valence electrons. Okay? What period is it in? It's in the 5th period because it's in the 5th energy level, or the 5th horizontal row in the periodic table. What block is it in? It's in the S block because, again, the valence electrons are in the 5s orbitals. So it's going to be in the S block because the valence electrons are currently being placed in an S orbital. So by knowing the outermost electron configuration, we can use information to predict where that element is located in the periodic table. Since strontium's got 2 valence electrons, the dot structure would have 2 valence electrons, or 2 dots, symbolized by the atomic symbol. All right, last thing. You might be given configurations of elements like this, where I'm not going to give you the whole configuration starting with 1s. Why? Because then you can easily count up all of the superscripts to get the total number of valence electrons and figure out what the element is. Instead, I might just give you the valence electron configuration and ask you to tell me where this element is located. All right? Now, the highest S tells you what floor it is on. So for this first element, 4s23d1, I know that the 4s, I know this element is on the 4th period. Okay, and the 4th period is the 4th row of the periodic table, which is the potassium row. Okay, the K row, potassium K, all the way across. This element is in the 4th row because it begins with a 4s. 3d1 and 4s2, if I add up the 2 and the 1, that adds up to 3 electrons, which means I would take that 4th row and I would count over. So up here towards the top here, let me add up, is scandium. All right, go ahead and do the next one and see if you can predict 5s2, 5p3, which element this is. It's a paper here, the periodic table. If I'm looking at potassium, this would be 1 element, 2 elements, 3 elements. 1, 2, 3. This right here, by adding the 2 and 1 together, that would mean there's 3 electrons that are in this 4th row, and it would be the 3rd element over 1, 2, 3 in the 4th period. And therefore this element (5s2, 5p3). If I look at the very last element, this tells me that this element has to be on the 5th row. P tells me it has to be in the P block. And 3 tells me it has to be the 3rd element in. So all that information, the last orbital, tells me exactly where this element is located. So the p block, again, is this row in which we have elements 13 to 18. The first row of the p block is p1 because it's the first column in the p block. P2 would be the second column. P3, P4, P5, P6. So P3 tells me I have to be the third column in the P block, which is group number 15, and it has to be on the 5th floor. So if I find the 5th floor, or the 5th row of the periodic table, which begins with RB rubidium, the 5th floor and group 15, where those two meet, that's the element that has this configuration. So if I go 5 over, rubidium all the way over, and 15 down, it meets at the element SB. SB has got the valence configuration of 5p3 because it's on the 5th floor in the p block and it's 3 elements over. And this is how we can figure out the element no matter what it is, simply by knowing the very last valence electron configuration. Okay? Your homework now is to do the next page in the packet, and you get some practice doing these where I can literally just give you one valence electron and ask you to tell me what element this element is. For example, if I said 5s2, 4d8, you should be able to figure out what this element is. Okay? Again, the highest number out in front, coefficient tells me this is in the 5th floor. So again, the rubidium family. The last orbital is 4d, so I'm in the d block, and I'm the 8th one over. 1, 2, 3, 4, 5, 6, 7, 8. So the 8th row over puts me 1, 2, 3, 4, 5, 6, 7, 8. This puts me d8 in the 10th group. So the 10th group, 5th row, where does that meet? And that is the element PD, palladium. Okay, so I really do recommend you do the homework problem and get practice doing these configurations where I don't give you the whole one, I just give you the valence shell, and from that you should be able to figure out where this element is located, even though you're not given the whole entire configuration. Okay? Thanks again for listening. If you have any questions, now this week at the end of the week you're gonna have quizzes. Again, you can take it as many times as you want to get as high of score as you want, but you're really gonna want to make sure you do the homework problems first and get the practice doing this type of stuff before you take the quiz. Otherwise, you're gonna have probably some low quiz scores until this stuff clicks. But again, the key thing is be able to identify what the element is based on this information of the very last electric configuration, last orbital or two, and using the information to figure out its location. Okay? Thanks again for listening.